In this video, I'm going to discuss some basics of machine learning in general, and we're also going to talk about the K nearest neighbors machine learning algorithm. So that's our first machine learning algorithm. So let's talk about the basics of machine learning. So what's our goal? Our goal is to train a model to produce useful response to the input. So we have an input, we want a response. The response is typically a prediction of something that we want to know about those data. When we input something, we get that response that's our prediction. And we can write in a very generic term, as you've seen, a formula like this, where we say our machine learning algorithm, which is a function f of x, equals y as our prediction. So x is our data cases that we have, and y is that prediction. If we know what those y values are when we're training the model, we call those the labels. And if we have known labels where someone has gone through and marked the cases so we know what the right answer is, we call that supervised machine learning, because the learning is supervised by knowing the labels. And in supervised machine learning, the features, which I've shown as x in my formula there, provide information to train the model. So those are one or more columns in, say, a data table that have that information. And the labels are those correct answers, as I've already said. Unsupervised machine learning, we only have features. We don't know the labels, and so we have to use very different techniques. And we'll get to unsupervised learning later in the course. So what's the process here? And we'll talk about this other parts of the class as well, because it's important to keep in mind that machine learning isn't just a linear thing that you just follow a recipe and boom, you're done. It's complicated. Things go wrong, and it's more of a scientific process, an exploration process. So the first thing is we have to acquire and ingest data. We have to explore those data. We have to understand the relationship, say, between the features in the label or between different features. And we'll get to that in another module of this class. We need to prepare the data so that there are not errors and other problems with the data. Another module in this class is going to address that, of course. And that can provide cleaning the data, feature engineering, and then splitting the data set. So we never want to train and evaluate or test the model on the same data. So we're going to talk about methods later in the class to split the data. And we need to then construct and evaluate a machine learning model. That's what we're leading up to with all this preparation. And when we find out, maybe we're going to find out that evaluation doesn't show us the performance we want, or there's some systematic bias or problem, well, we may have to repeat many or all of the steps above until we get where we want to go. So let's talk about our first machine learning algorithm in this class, which is what we call the K nearest neighbors algorithm, or KNN. And it's a really simple method. It's been around for a very long time. In many cases, it's still very effective. It doesn't require any particular training. It's a little odd. It needs labels to know what the cases are, but we don't train on those labels. It's just whatever the data are, they determine the nearest neighbors. So it's a little bit of an outlier in terms of other machine learning algorithms that we'll deal with in this course. A new case, so we have some known cases, known label. We get a new case, and we find out where it is in the feature space, and we look around and we find some near neighbors, and we use the ones that are in the nearest proximity to our new case, and to find out how to classify or predict that new case. And we have to use a distance metric, right? So I've been talking about proximity. Well, I need a distance metric, so I need to measure distance from my new case to existing cases where I have marked labels. And most commonly we use Euclidean distance, but other distances are used. We can also use weighted distance. We may care if one case is close to another. We may want to weight that higher than one that's further away. And K, the K in the K nearest neighbors, or KNN, defines the number of neighbors we're going to use to make that prediction. And the basic algorithm then is really simple. Once we know how to compute the distance and weight or not weight the distance, we basically go for a majority vote. And that's the label that we are forecasting or predicting for the K nearest neighbors algorithm. So let's look at an example here. So I have these data on my screen here, and you can see there's red triangles and blue dots. And let's try the K equals 1 case first, okay? And I see the little question mark just appeared in the middle there. And I want to know how I'm going to classify that data case. So I have my two features, you see the vertical and the horizontal axes. So there's two features in this. And I need to find the nearest neighbor, and we'll just use Euclidean distance in this case. And so we draw a circle there, and we find that as the circle expands, here's the first case we hit is a red triangle. So we classify this question mark now, we say, oh yeah, that's a red triangle. But we could also say try K equals 3. You can try different values of K and see what works best for your application. And now we get this bigger circle because we have to inscribe the first 3 data points we encounter. And it looks like in that case, the blue dots win. And so so it's quite different result we get here between K equals 1 and K equals 3. And which is better, you'll have to evaluate and see. And you'll get a chance to do that in the lab. But there's a problem with K nearest neighbors, and this pervades all machine learning, but it's really evident here. It's an effective classifier when it works, but it suffers from something we call the curse of dimensionality. And let me just give you an example so you can wrap your heads around what this problem is. So in one dimension, say I just have one feature, so one dimension, and I have 10 samples. Well, I have maybe that's dense enough sampling of my known cases, and I can get a pretty accurate classifier. But if I want that same density in 2 dimensions, which is like the case I just showed you was 2-dimensional, I need 100 samples. If I have 3 dimensions, I need 1,000 samples. 4 dimensions, I need 10,000 samples. So if I had 10 features, I'd need 10 to the 10th samples, which is like it's like 10 billion samples to get the density of my 1-dimensional case. So and this is what we call in machine learning the curse of dimensionality. And it affects all machine learning, as I said, but it's particularly a problem with algorithms like K nearest neighbors. So just keep that in mind when you're working with algorithms like that.